but I'll get to that in a little bit. You're going to get a copy, because it's included in the material that Mike's going to copy, of a handwritten reconditioning report I did back in November 25th, 1955. That's a little earlier than some of you can remember, I'm sure. Where you go out and test the well and you can put your thumb on the orifice plate, because it only had 7-pound shut-in pressure at the time. And that whole area was on vacuum for a long time, so the idea of PWF equals 0 isn't absurd as you think. I could have used the -5 and still been in the ballpark. But what I ended up finding was there was wells out there that when you'd shut them in, the rate would practically drop to zilch, and the shut-in pressure would change. A high shut-in, well, these are some of the conclusions I was drawing from some observations out in that area. A high shut-in pressure indicates the well needs reconditioning. The Grayson, a lot of these old wells were all completed open hole. And the granite wash is about what it indicates, a very, very high permeable sand at the bottom of the well with a brown dolomite above, which was open hole. The wells were never stimulated. After the reconditioning, you got 50 pounds. We went from 140 to 50 pounds. And at 140 pounds, it might produce about 10 MCF per day. At a 50-pound shut-in pressure, you produce about 1,000 MCF per day. What was able to figure out really was we really had a true layered no crossflow situation then. And what we were getting, this was the shut-in pressure of the granite wash, the high perm layer. This is the shut-in pressure of the low perm layer, the brown dolomite. The 10 MCF per day was what was with a flow rate coming out of brown dolomite, and 140 to 80 at this time. And Magnolia is mobile. Shamrock's out there, but you can see the variation in the shut-in pressures on some of these wells, but the consistency of the 40 and 50 pounds of the granite wash. So way back in 1955, I was seeing this phenomena. I didn't understand or appreciate the implication. But one of the things that also kind of saying is, hey, there might be a way by putting something in a wellbore that I could kind of get these two-layer properties and pressures and flow rates separately. Something to think about. I showed you before, I'll reiterate again, the wall, but we've got them all on a common plot. This is Morrow, over 2,000 pound shut-in pressure in 0.9 or 1. You see the very rapid drop in P over Z, and you see a nice back pressure curve that's steep. It could be due to the layering effect. So we see all of these characteristics on one place. And mentioned to you earlier about, well, we thought maybe this was a true composite reservoir that we had drawn on a board before, until they went in and ran RFTs on that well, the wall. And there's 9 feet of pay, sand. At the top we were recording 550 pounds, at the bottom 623 pounds in 9 feet of pay. You show me on that log where you can see that there's a clear distinction, that there is layered no crossflow behavior. Remember, this can't be just at the wellbore, this is throughout. Otherwise it would equalize back here a little bit. Okay? So even though we're kind of using the rule of thumb, in generally thick you can almost be sure, you can even see it in thin. And you see how clear why we do these types of plots? How clear it is on here in all ways that we were trying to describe in terms of rate time, in P over Z. Every single indicator of layered no crossflow is on these graphs, and this is why we look at everything. You just don't look at the P over Z. You look at this and plot log, and look at the back pressure curve. And there's real clear evidence. And see, we can produce 1,000 of these plots within about an hour or so on a computer in Bartlesville. Now, I'm sure you can do it here too. But you don't have the same problems, other than remember, the technology applies everywhere. It just isn't confined to the States. It is everywhere. Layered no crossflow. Start looking for it and you'll see it. Like I mentioned earlier, if this was oil, you might say, hey, that's a very highly undersaturated. We're dropping one of the papers that you're going to get, and I don't know if you're going to get them before you go home. Hopefully you are, and you can take a look at them, and you might you'll be able to come in, you discuss them. You ought to start looking in these papers for layered no crossflow reservoir responses and what to do about it and where all it can exist. You'll see some in shale reservoirs. You completely shale. You're going to see the same phenomenon. Do you see something here? Do you recognize this maybe a little bit? Drawn by a geologist. The pods, you see pods again? What happened between here? This is carbonate. The picture is almost drawn to lead you to the conclusion that it's aerial discontinuities. The other thing, well, it said, well, this is how we were doing reservoir engineering. This was our problem. We were considering everything homogeneous. Yeah, but then now we draw pods, like I say, well, this sort of explains everything because we have these aerial discontinuities. The way the figure really should have been drawn in the first place, and I used the same color code. That's how it should have been drawn. Just like there. There's no discontinuities between here. The layers are continuous. The properties may change. The real key is in the vertical. You can't see vertical layering in that other figure, could you? These carbonates are just like those carbonates, even though they're a little deeper. They're exactly the same. All carbonates are basically the same. If you stopped your wells, if this well had been stopped here because you saw an oil water contact here, and you saw an oil water contact here, and you didn't drill these wells deeper, you'd have found new oil, wouldn't you? Why? Because layered no crossflow. What was wrong? The other diagram implied carbonates are naturally fractured, and they are buggy and naturally. It's in total vertical communication. So that's the way everybody was kind of looking at the problem. But see, then they explain all the infill drilling that they did to get additional production in this field by aerial heterogeneity. And we're going to try and work through an example tomorrow. I'm going to show you I'll get the same picture that they get. We'll produce identically the same picture. This is for lease, but we're going to do it for well. You're going to get the same type of a production. You're going to come down, you're going to do an infill well, and it's going to go up. It's going to come down, and you're going to do a couple more infill wells. You can go from 40 to 20 to 10, and it's going to go way up, even higher than here. Just this, a two-layered system with each layer being perfectly homogeneous. We're even going to go through the calculation that you're going to calculate by hand the interference effect as a result of the infill drilling. And if the permeable layer was on the bottom, it's about 200 pounds, and the other one is about 750 pounds. 750 pounds, what are you going to conclude? Aerial heterogeneity, pods, wouldn't you? And it's layered no crossflow. They try and explain it. There's a famous figure that's published in those papers about the continuity. Well, there might be a certain degree of that, but I don't think it explains it all. I think, again, layered no crossflow is really, they keep saying about percent continuity and your 40-acre wells and how continuous it is, and if you keep drilling more, you find it was more discontinuous. Isn't it amazing, though? You can go from 40 to 20 to 10, maybe even 5, and each time you keep getting wells in a layered no crossflow system with one or more of the layers being low permeability. that's what we're going to try and, for one of the examples I'd like for you to work through, just to kind of get a feeling for that problem. In a way that you go, as far as I'm concerned, logically, the way you go, get to this figure, how do you really get to this figure from a reservoir engineering standpoint? Well, you take this figure and you assume cross-flow. And once you assume cross-flow, everything's going to act like a single-layer homogeneous system. Yeah, it's important that you sort of understand that concept, that that's what was really being assumed, because you go out at any cut, anywhere, look at layers. Layers are everywhere. No one ever really envisioned that you can go to this type system. It'd be blanket, but that would be exactly identically equivalent to this if you assumed there was cross-flow between each of the layers. You get this, the same physical model. I'm going to show you that I mentioned earlier about work that Tramco is doing on Ghost River. A carbonate reservoir in Canada. These are the 4 wells. They were drilled. We've sat on that sucker 10, 15, maybe 20 years trying to determine whether we should develop or not. These wells were rigorously defined. All the geology was drawn. It was about 100 billion. That's the number I remember, but Tramco puts in 89. To me, 8,900 is the same. That was used, and the wells were drilled, tested, stimulated, so we exactly had the deliverabilities. The runs were made on 7151, with everything in a tank. These are roughly the permeabilities kind of on a regional basis, because you can look at this both as close to the south 0.08, almost a factor of 10 again. So you have it even looking at on a regional basis or on a layered basis. You got that 10-to-1 contrast. I think I showed this to you before. I'll show it again. This was the AFE forecast. 7 years at a constant rate and then go on decline. This has taken all of this information and doing a sophisticated risk analysis of the problem. This is where you would come to on a rate time, and this is actual production. It's exactly what you would match using the deliverabilities of the well in a 2-layered reservoir system, and all the gas that was mapped, 100 billion, exactly reproduces that from a layered no cross-flow standpoint. If you'd use the actual deliverabilities and what gas in place would I require with a single tank model to get this match, you'd have to cut the gas volume from about 100 billion to 50 billion. And then the red flag goes up. This is one of the criteria. Is what happened to the gas in place that we mapped? Well, it's stuck in here in layers. You can't see the pressure. That's what it is, and we can exactly reproduce. And we ran production logs, and let's see if we can drill a horizontal well in this region and do that, and we ran that case, and we just couldn't change it. We couldn't change the economics. There's anything we can do. We're stuck with that field development. It isn't very economical. We could prevent it now. We were involved in looking at an adjacent field next to the Chatham Reservoir in Alabama. It's a deep, high-pressure, rich gas condensate. That one of the owners was saying that we're being drained, or that reservoir is being drained because of development of an offset field. And the field has been cycled. Okay, it's been history matched. It's been cycled. It is basically described as a minimum of about a 3-layered system. And when you take the model and go back to the beginning and produce it like it produced against the constant wellbore pressure, that history-matched model that has never been on decline. It's been cycled from inception would reflect the B value 0.7. The significance is if you then take that rate time and plot it on a semilog, you see where you're dropping off the end of the table. It looks like you would be being drained. You know, that you're losing gas somewhere. If you take that a model and plot the volumetric average pressures out of the model, it's actually a 6-layer system. So this gives you an idea. This gives you an idea of how the pressure versus cumes would look on each of the individual layers. You know, there's layer 1, which is the more permeable. Layer 2, slightly more, and just you successively go up, and this is going to be the lowest permeability layer, or Qmax over. Again, I'm saying that assuming skins are equal. Remember the Qmax over G sub I ratio. This is the way it would look, and this is the way you can present data out of your model in terms of you're trying to get people to understand layered no crossflow. And it shows the pressure difference. These are 24-hour bottom hole shut-in pressures, and you can see where they match with regard to the more permeable layer as compared to the other. Out in here where you're looking at the more permeable layer around 1,500 pounds, less permeable, or the lowest permeable is around 4,000. I think I showed you on, well, this is an updated one on the Red Cave. I don't know why that's there. This is an updated performance plot on the Red Cave. Again, and you can see the line pressure changes. Look at that. Wouldn't you just intuitively say this is what the consultant gave us on a total field basis, and why he said, yeah, this is it's obviously exponential decline. You take that data, plot it log, it isn't obviously an exponential decline. It's got a B value of about 0.9. This is a recent well that was drilled in the Texas Hugoton field. Kreider, layer pressure is 85 pounds. To Harrington, you get 235 pounds. Now, this is way south of Oklahoma. We're into the Texas Hugoton. I've seen data that some operators were thinking about going in to ask infill drilling. The same thing's happening in the West Panhandle field. You see these same types of pressure differences. I think that is in the Texas Hugoton. It very well could. No, it can't be in the West Panhandle because that shedding pressure is too high. West Panhandle is about 20 or 30 pounds. Yeah, so it exists everywhere that you start looking for it. I mentioned to you earlier about this fellow Redmond worked for a company overseas here. He was a chairman of the session out there in the Panhandle where this paper was given, and this fellow was saying, Fetkovich developed the technology, but we're the first to apply it. San Juan Basin, well over 1,000 feet thick. The original wells were completed open hole. They were shot with nitroglycerin. You solid nitro, they weren't even acidized. 26 MCF per day. After sidetracking, remember sidetracking. They just moved over a little bit and re-drilled the well. They didn't move over and drill an infill well. So they can case and individually frack up and down the hole from 25 MCF per day, average well, to 635. If you accomplish this by re-drills and moving the well over in, say, the middle of the section, I mentioned earlier, the conclusion was, boy, look at this is a case for how easy you could have got into that trap of the reservoir characterization aerially. I keep running into this overhead. I think I've already shown it, yeah. Using the equation with the time that you get as compared to the 3D model. I must like that slide. I have it in several places. Oh yeah, this is a beautiful one. This is one in Kansas where the operator's using new technology, really fracking. Yeah, the wells, big frac treatments, lots of sand, lots of fluid. This is the deliverability of the original well. This is the deliverability of the infield well, and they're all that way. You be careful. They thought they were applying the most modern, newest technology, so it had to be good. They weren't even measuring the performance. They didn't even know what they were getting. Running a model, getting a frac design, and saying this is the best. Actually, well, you know, we were talking about rate decline. When you get into high pressures like this one is around 6,000 pounds, a Puckett Ellenberger, tubing limited, the well deliverability has a slope of about half, which means it's all friction drop through the tubing. If you got a half slope, you can predict a B value 0 in the production rate, you know, but almost a perfect exponential decline. It's expected. You should be able to expect that. You know, one of the things we were saying earlier